So chapter 5, relations. So definition, given a set A relation on A is just a subset R of A cross A. What was A cross A? All right, A cross A is equal to what? Or A Cartesian product A. Come on, guys, dig. What was it? Oh, yeah, I guess it kind of looks like maybe I want to do matrix multiplication, but it's not it. Cartesian product. Come on. It's the set of all what? It's just like the two-dimensional plane, right? In the two-dimensional plane, you take pairs of real numbers. Here, we're just taking pairs of not real numbers, but pairs of the set. Yeah. Set of all pairs, x, y. Ordered pairs, right? There's a first coordinate and a second coordinate, such that x and y are both elements of A. Right? This notation, however, is not really used. This notation is not really used. Rather, when x, y is an element of R, which is a subset of A cross A, then we write x is related to y, and we use this twiddle thing here, which is said x is related to y. By the way, this is a definition. Okay, you gotta spend time with it. You have to spend time with the definitions. Get to know the definitions. So, for example, I mean, it can be just about anything, but we've looked at quite a bit of different types of relations throughout your whole educational career. Given a set A and its power set, PA, okay, define x so for x and y elements of the power set of A, in other words, subsets of A, say that x is related to y when x is a subset of y. In this case, we don't use the twiddle, we use subset. When talking about this kind of relation, okay, we don't write. Well, when talking about a specific type of relation like this, we don't write x is related to y like that. We just write the specific relation symbol. X is a subset of y because it's a very specific relation. So instead of being non-specific about it, we be specific about it. Given a function f from a to a, say x is related to y as elements of a, when f of x equals y. So I mean, it's just about any sort of thing you can think of. I mean, becomes a relation. Here's something given x and y in the set of natural numbers. Say x is related to y when x is less than or equal to y. Okay, again, we use x less than or equal to y rather than when the relation has a notation, we use that notation rather than the twiddling notation. But another relationship on the natural numbers given x and y in say x is related to y when x divides y. So this relation is often written as follows. So it uses that vertical line, kind of like the such that thing. So, and anyway, just the plain old definition of relation is pretty boring because, I mean, you can just define relations however you feel like it for the most part. There are specific types of relation, however, that are very important and come up a lot. And then to hint at one of them, here it is. So, given a set A, we say that subsets A1, A2, AN, and A partition A when each AI intersect AJ is empty, or I not equal to J. In other words, the sets are disjoint. Okay, we say that these subsets partition A when the subsets are disjoint and their union equals A. All right, in other words, A1 to AN partition A when A is the disjoint union of A1 Jn. So that's the notion of a partition. And when you have a partition, so now define a relation E, subset of A cross A, E on A, by X is related to Y when X and Y are elements of the same AI. So every element of A is going to be in one of the blocks, so those are called the blocks, in one of the blocks of the partition. Every element of A is in one of the blocks of the partition. You say X and Y are related when they're in the same block. And they're not related when they're not in the same block. X is not related to Y when X is an element of AI, Y is an element of AJ, with I not equal to J. So a partition relation. This type of relation, partition relation, has some very special properties. So here's the definition. It's not called a partition relation, but it's called an equivalence relation. So a relation, twiddle, on a set A is called an equivalence relation when it satisfies the following three properties. One, it's reflexive. Reflexive property for all X in A, X is related to itself. Two, the symmetric property for all X in A, X related to Y implies Y is related to X. So X relation to Y and Y relation to X, they're equivalent to each other. So for example, like on the natural numbers, right, when you say X and Y are related when X is less than or equal to Y, is that symmetric? If X is less than Y, it implies that Y is less than X. Is that true? Or when X is less than or equal to Y, it implies Y is less than or equal to X. Is that true for every X and Y of the natural numbers?
No.
No, it's definitely not true. It's never true, actually. The only time it is true is when what? Are we doing digraphs? One can think of them as digraphs. One can think of them as digraphs. I wasn't going to get into graph theory in the course, but yeah, you can think of them as such. So X less than or equal to Y does not imply Y is less than or equal to X unless X equals
Y equals X?
Yeah, unless they're actually equal. So like this type of relation is definitely not symmetric. Equivalence relations are. So this is not like what we're talking about here. Same thing with like subsets, right? Like A is a subset of B does not imply B is a subset of A unless, right, A and B are equal as sets. Right? So subset relation is not equivalence relation. Equivalence relations are something different. Three, so reflexive, symmetric, and transitive. For all X and Y, for all X, sorry, not for all X, for all X and Y in A, and this is for all x, y, and z in A, x related to y and y related to x implies x related to y and y related to z implies x is related to z. X related to y, y related to z implies x is related to z. Given an equivalence relation, so let's show that this relation, this partition relation, is an equivalence relation. All right, consider a partition A1 to AN of set A. Define a relation on A by x is related to y when x and y are in the same AI, in the same block of the partition. When x and y are in the same block of the partition. Prove that this is an equivalence relation. Okay. Reflexive. So to be an equivalence relation, we have to be a relation that satisfies those properties above: reflexive, symmetric, and transitive. Okay, so symmetric. Is x related to x for every x in A? If you take an element x in the set A, is x and x in the same block of the partition?
Yes.
Okay. Now, I'm glad you said it, and I'm glad you said it fast. What I said there, okay, is, so this is something you also have to get used to in mathematics, is when people want you to state the obvious, state it. Okay, because it's important to state the obvious. So this is obvious. I mean, if you've got these blocks, right, A1, A2, A3, A4, and, you know, element x is in A2. Okay, so if element x is in A2, then is x related to x? Are x and x in the same block? Well, yeah, of course they are. Okay, I mean, it's stating the obvious, but unfortunately I said the obvious in a complicated way. Okay, but there's a lot of that kind of goes on sometimes, stating the obvious, because sometimes it has to be said. Okay, certainly. Just, I mean, there's nothing to be said really. X is related to x for all x in A, because x and x have to be in the same block, because x is itself. Symmetric. What is the symmetric relation? X related to y implies y is related to x. How do you prove x related to y implies y is related to x? Well, how do you prove an implication is true in general? How does one prove an implication is true in general? There's three ways.
So the conclusion must
Direct
also
proof.
be true?
What's that?
I was just saying you assume the hypothesis is true.
Yeah, you assume the hypothesis.
And prove the conclusion must be true.
All right, so if you're trying to do P implies Q, Direct proof is assume P, show Q. Contrapositive, assume Q naught, show P naught. And contradiction, assume P and Q naught, find a contradiction. Find R and R naught within the statement. Okay, so again, stating the 3 ways to prove a implication statement. Direct proof, contrapositive, contradiction. Super important, super duper important. Okay, anytime you're trying to prove an implication statement, the first sentence of your proof should give away one of these 3 things. Assume P is true. This person is doing a direct proof. Assume Q is false, or assume Q naught is true. This person is doing contrapositive. By way of contradiction, assume P and Q naught is true. P is true and Q is false. This person is doing a contradiction. No matter what level of mathematics you're talking about, I don't care if it's this level of mathematics or cutting edge research at the very highest level of mathematics at anywhere in the world, it always is that. The first sentence of the proof gives away exactly what type of proof you're doing. Unless there's something important to say beforehand. Here goes nothing, Geronimo, whatever, So we got to prove X related to Y implies Y is related to X.
I do have a question.
Yes.
How do we get it to where we're not as wordy? Because I think that's like one of the things that is not good is we tend to write our proofs very wordy because we think they're very elegant.
The first time you write a proof, it may turn out to be wordy. So you kind of have to go over it again and think to yourself, did I really need to say that? Am I repeating myself? Wordiness is often, is a function of 2 things. One, you're kind of belaboring the obvious. Sometimes you have to state the obvious, but when you're stating the obvious, make it quick. Okay, don't go on and on and on about it. So this reflexivity thing is obvious. So certainly X is related to X. Okay, if you kind of don't see that, then you have to go back to the proof or the definition and try to understand why it's for certain or why it's obvious. The other thing is you could be repeating yourself. Right? So when you go back and read and look, did I say the same thing twice? Did I say it one way here and another way there? So avoid repeating yourself as well. And then things will get much more condensed. Right? Just those 2 things will help tremendously. Is that clear, Brooke?
Yes, I know that's something that we try to strive for, is making it as simplistic and as to the point as possible.
To the point yet complete. It's excusable if you're not sometimes. But I'll point it out certainly if things are wordy. Okay. I haven't seen anybody get wordy on me yet. All right. So assume X, we're going to do direct proof. Assume X is related to Y. That means what as far as this partition goes? That means what? Come on, guys, right here. X twiddle Y when X is related to Y when
X and Y are elements of the block of A.
the block AI for some I, which means does X and Y being in the same block, does it matter if I say X and Y are in the same block or Y and X are in the same block? Does the ordering matter with sets? When you say,
No.
no, it doesn't. Right. I mean, if I said 2 and 3 are elements of the natural numbers, you'd say, yes, that's true. If I said 3 and 2 are elements of the natural numbers, you would say, yes, that's true, but why did you say them in order? Well, you don't have to. There's no law against it. Okay? So, when you're talking about elements belonging to a set, remember, sets have no particular ordering to the elements unless you happen to have one added on. Okay, transitive. So with transitive, X is related to Y and Y related to Z implies X is related to Z. So what am I going to assume? What do I need to assume?
That there's a third element?
Well, it's an implication statement. There's 3 ways to prove an implication statement. It doesn't have, the X, Y, and Z don't have to be distinct, by the way. They could somehow, X is equal to Z, X is equal to Y. That could be the case. So it's an implication statement. P and Q implies R. So we want to prove P and Q implies R. First sentence, you've got to give away one of 3 things. Direct proof, contrapositive, or contradiction. So to prove P implies Q is true, there is the direct proof. Assume P, show Q. There is contrapositive. Assume Q naught, show P naught, and contradiction. Assume P and Q naught, find R and R naught. Alright, so we're trying to show the implication is true. That implication right over there. Oops, that's too thick. So 3 ways to show an implication is true: direct proof, contrapositive, contradiction. So I'm trying to show x related to y and y related to z implies x is related to z. So what's the first sentence of that proof? You guys watching YouTube, or are you all with me? You all here? So I'm trying to show that this implies that. What's the first sentence of the proof? Y does not relate to z? X relates to y and y does not relate to z? Why the not on the second one? Right, the hypothesis is these are both true. Right? X relates to y and y relates to z. So you want to assume this and this. All right, so assume X is related to y and y is related to z. This means that what? X and y are in the same block, AI, and y and z are in the same block, AJ. However, AI and AJ are disjoint if they're not the same. Right? So y is in AI, but y is also in AJ. Right? But since the blocks of the partition are disjoint, since the blocks of the partition are disjoint, we must have, and y is an element of AI and y is an element of AJ, we must have that I equals j. So x and z are in AI. Thus, x is related to z. I probably said too much there. Like right here, since x and y are in AI, and since you're talking about y again, it's got to be AI. That's probably belaboring the obvious what I just did, but it's not too bad. It's not too bad. All right, try this one for next time. So for next time, prove that the following relation on Z is an equivalence relation. All right, so say X is related to Y when X minus Y is even. Okay, prove that's an equivalence relation. X is related to Y when X minus Y is even. And then you can use the fact. Well, I'll leave it up to you to think about that, okay? All right, guys, have a good day, and we will talk to you on Wednesday.